Good morning everyone, welcome back to our channel. Today we continue with our programming course and we will dedicate a moment to direct programming examples. So I won't teach you anything new compared to what I taught you in the last video, but let's say there's nothing better for learning than to walk the path. So let's do some direct programming examples to ensure that if what I explained in the last video wasn't clear in theory, we can make it clear in practice. On the left side of your screen, which is my right, but we are going in reverse. I apologize, but I see the camera reversed compared to you. You will find examples that I have conveniently written on the board. And now, regardless of the spindle rotation, the preparatory functions, and the turret rotation, we will, as we did in the last video, go through point by point. The drawing we see on the screen, always starting from x0, z0, which in reality makes no sense, but is convenient for us to learn. So, first drawing, as always, we draw the origin of the axes and start from x0, z0. What do we need to do? We need to go up. Do we have a diameter? Well, yes, we have it because we have a diameter of 33 and a chamfer at 10 degrees that starts 2 mm below the 33 degrees. So, will we stop at 31 degrees? No. I already explained it to you. The measurements we see as radial, not diametrical, need to be doubled. So we will stop at x29. Therefore, we go up to x29. 0 remains 0, after which we start moving by using the angle function. So we go up and are at x29. At this point we say move, tilt 10 degrees. We set a barrier at 33. For now we set the barrier as dashed. The degrees we set as dashed. We are, having arrived this far, what do we say? Barrier x33, angle 10 degrees. No, because the angles are from 0 in this sense. So our 10 degrees become 180, at least 10, angle 170. Therefore, our machine will start moving to x33, inclined at 170 degrees. Perfect, that works for me. Now what do I need to do? I need to move to Z16 while staying at x33. So Z16 is here. We fix the point and tell it. D16. At Z16, what do I need to do? I have a perfectly tangent arc to both the incoming and outgoing air of 6. Okay, at this point, what coordinates do I have? From that point here, I have, let's see, 30 degree, 60 degree, but I have neither X nor Z. What do we do? Let's do this. So, we are here. We know that from this point we need to move upwards at 60 degree, 180 degree minus 60 degree, so angle 120, 30, 60, so angle. The machine draws its line, and here it draws its arc, so it can already reach up to here. But at this point, its 120 degrees are infinite for it. I haven't given it any final reference point. What does the machine tell me? However, the machine tells me, the drawing, that I will have to reach here at some point, which is x90, z minus 50. x90. So minus 50. Let's fix it here at this point. The machine is at the point. The two lines are not coincident. And what do we need to tell it? We need to tell it that we have an angle of 30 degrees, so 180 minus 30 is 150. The machine in its electronic brain reasons backward, so it draws an inclined line of 30 degrees. You see that now the machine in its head has all the perfect building elements. That I can get here. So this is the point x 90 z minus 50. Well, I can give it the final z, which is z minus 64. As you can see, it's very easy. If I can draw it, look here. I can program what happens in the example after the previous one. If you look, it's very similar to the previous line. The only two differences. Let's see if I'm not mistaken. No, well, there isn't a radius. So, you see that it didn't quote the 2, but quoted a chamfer 3 for 45. So, we need to redo it. Let's put in some goodwill and redo it. Maybe it was better to do it next to. See the differences. You see that here? It doesn't quote the 2. It doesn't quote chamfer 3 for 45 x33. So, from here, I go to x33 and I tell it chamfer. So C3. Here the machine, what does it do? It calculates up to x33. It no longer has the 10 degrees. Wait a moment. And it asks what the next block will be. The next block is 1z16, which means it will stay at x33. So, what does it do? It takes these two trajectories, cuts them, 3 and 3 meter, and constructs its trajectory. Here I follow the same line as what I did before, so I don't have the intersection point of these two lines, but I have the degrees, so A120, and then I have the final point, so x90, z minus 50. So what do? I construct a line at 60 degrees, take the final point, which is x90 z minus 50, and I add these 30 degrees, which means a 150. I construct the line. This is the intersection point on which I have a bevel, because it is a bevel all around, meaning it cuts a trajectory that is equal to the real one. Vertex of 5 mm. So 5 mm here and 5 mm here. Then I add a C5 here. What does the machine do? It takes this trajectory and follows it. At this point, it stops 5 mm before the intersection of the line, makes a rapid trajectory 5 mm beyond the intersection and continues at 150 degrees. That is 30 degrees. At this point, I put my Z64, as you can see. This can also be drawn. I gesture off camera. But the important thing is that you hear my voice. It can be drawn. It can be programmed. It's very simple and beautiful. What comes next? If you have a good eye, you can see that my little programs are already filled in here. But I'm not reading them. So if I'm making mistakes, you can catch me. Here's an example of a mistake I'm making. But it's not a mistake that some CNCs require a comma before C and also before R. I had mentioned this to you in the direct programming. But what you need to understand is the method. Very well. X0, Z0 is always him. X. 76, we are here. And C3. This should now be very familiar to you. So I'm here, I go up and make a chamfer. And then from here, the fun begins. We already tackled a similar little program last time. 15 degrees down, which means 195 at 195. a fillet of 13 meter, so R13. At this point, what does the machine know? It knows that I have to descend at 15 degrees and sooner or later start a radius of 13 millimeters. At this point, the machine says, okay, where do I stop? You stop at x90z minus 50, so here. x90z minus 50. How do you get there? You get there at 30 degrees, so 180 minus 30 is 150. I'm here. Machine goes back. Take its nice 30 degrees. It begins to understand that this is the point of intersection of two lines, and that here it will need to make its connection thus perfectly tangent, and its trajectory Z64 is drawn. Let's see what we have next. There are other interesting examples that we can explore together, diving deeper into each one to understand their unique aspects and applications. I would say that we have almost covered all the examples I have prepared for you after this point. So let's take this particular example here, and let's try to make a slightly more realistic and complete example that encompasses more details and intricacies. So I won't draw the piece, but instead let's write a program, as the machine should do, in a real-world scenario, considering all the variables and conditions that might affect the process. Let's say this piece is already pre-shaped, pre-roughened. We need to finish it and work on it to bring it to completion, ensuring that every step is meticulously followed. So first of all, we need to consider the percentage of 100 or percentage, and we call it example, which serves as a reference point for our operations. This is how Fanuc might name a program, with its comment, providing clarity and context, ensuring that the program is easily understandable and executable. Then we say G92, S2000, however it goes. You never exceed 2000 RPM to ensure safety and precision, which is crucial for maintaining the integrity of the piece. It's a light piece, and we will work it in M42, which is a specific mode designed for such operations, ensuring optimal performance and results. We want to be safe, so we wait a second, then proceed with M42, and we call turret TO10, which is a crucial step in the process, ensuring that the machine operates smoothly and efficiently. Perfect. Let's slowly and precisely rotate S300G 96 degrees in a smooth and controlled manner, ensuring accuracy and precision. Let's go ahead and cancel it, because I told you, and sometimes I forget too, that first of all, you need to tell the machine how to think about the feed rate, G95. All our F values will be given in millimeters per revolution. At this point, we start the self-centering M4 S300 G96, which means that S300 is the meters per minute of material that will develop at the tip of our tool in relation to the diameter we will be working on. The order of these lines doesn't change much. Ideally, it's always good to remember to put G95 before M4, but it doesn't matter if you change it later. So, don't worry about the order in which you enter these codes. Okay, here's M42. The range must be entered with the spindle stopped, so M42 should always be placed before M4. Otherwise, the spindle stops, changes the range, and restarts. Let's say it's a bit stressful for the machine, not so much for the CNC. Okay, the first operation to do is to face this piece. So the approach to the machine can be something like G00 Rapid X35 0.5 Z0. What happens If my piece, this is X35, this is my 0. If my piece protrudes, I don't know how much it protrudes, 5 millimeters, and my colleague left the machine here. We do this, and obviously we collide. So a correct approach could be something like X200. I raise the carriage everywhere. I raise to X200. I leave X0 inside, GO0, and I move to 0. And then to X35. So that I have mistakenly erased the piece. This is my 0 piece. This is my piece that protrudes. What does the machine do? It is here. It raises to X200, moves to Z0, and descends to X35Z0. Excuse me, it moves to Z0 and descends to X35. I will not have a collision in any way unless I have machines with particular internal configurations, such as protrusions or obstructions caused by specific equipment. However, that cannot be seen in a course. All that exists in a machine shop. At this point, I move on to G1. I enter X minus 0.8 because I already mentioned it. If I have an insert whose tip radius is 0.8 and I go to X0, this part of the steel will not be removed. So I lower my tool by 0.08, 0.8 more. Small reasoning. I said 0.8 more. Sorry. This is the radius, 0.8. You see? Sometimes I get confused too. Minus 1.6, twice the radius. Okay? Of course, I need to set an F 0.2, meaning for each turn of my self-centering tool, I lower by 0.2. If you don't have the tool perfectly aligned, it's better to go down to F02 until X5, and then slow down to F01. Then I add a magical M8. I'm writing too wide, I think. We won't reach the end of the board. M8 enables the coolant. M9. I'll tell you right away, because I might forget. Turns it off. And this is more or less true for all CNCs. At this point, I reach the end of my roughing, GO0, Z2, X35. I bring myself here in front of my piece, ready to start. Do this because I didn't take the spaces into account. So M8 or coolant, during rapid movements, I can decide whether to keep the coolant on or off. Well, I'm here. I need to switch to GO1. Go to Z16, ending with a radius of 6. Now, L1, GO1, F02, if I do not modify it, the machine will remember the last programmed movement and advancement F02. Okay? If instead I want to modify it to F03, the only drawback of direct programming is that I cannot do the cylindrical part and the radius with a different advancement unless I stop appropriately beforehand. So programming 1Z10 and then 1Z16R6 with 2 different F values. Okay? In that case, I can do it. If I make a mistake with the arrival point, the machine will give me an alarm so I will have to backtrack a little. So if I stop after the start of the fillet, let me explain better. If I have to do this, the intersection is Z16, this point should be Z12, and I program Z13, then Z16 R6. The machine will give me an alarm because it says no, I cannot start tangent here. Well, I have arrived at Z16 R6. What do we do? As we did for the SIL program before, because this is very similar, we give it the angle. Angle 180/60 equals 120 with a final in R12. I no longer need to repeat GO1. There is no necessity. A and R are not like GO2 and GO3. It is a GO1 for the machine that simply transforms into direct programming. Now what I need to do is no more and no less than before. Give it the final point, which is X90Z 50, angle 150 R, not R, pardon, C5, because this time we finish with a bevel. Okay, at this point you can see it well in the drawing. Here we have the perfect R12 Z64. I have completed the entire profile. At this point, I exclude GO1 with a nice GO0. I'll put 92 on it. At this point, I have finished the machining. I put in an M9, so I exclude the M8 and stop the coolant. GO0 X200 Z300. I move away. M5, I hadn't explained it to you yet. Stops the M4, so it stops the self-centering. M30 tells the machine I have finished. From the next start, you restart here. A small digression that I always confuse. So I need to go check, or I'll get mixed up. And this is because I really use them very little. The U and the V. Let's add something. Let's learn something here as well. X equals U. Z equals V. Our machine can move in two ways: absolute and incremental. Absolute, this is my reference axis. I give my X and my Z relative to my point 0, 0. So Z minus 10, X 10. It will be here. If I now want to go to X12, I have two ways to do it. Right, X12 or U2. U2 is an incremental, meaning that relative to the point where I am, the machine moves by only 2 millimeters. Likewise, if I want to go to Z15, I can write Z15 or V5. I am used to using it very little, but it is important to know it because in certain situations it is really convenient to do so. If you are like me, forgetful and don't remember it by heart, because I swear I've been using them for years, and every time I have to open my notebook and say X is U, Z is V, those who use FANUC are lucky, because on the FANUC users who have them one above the other on the keyboard, making it easy to remember. So remember, U is the incremental of X, V is the incremental of Z. Always check in the machine's free mode if U is expressed in a radial or diametral way, because for example on the Philips 432 coupled with Imao, I give this example because many have been sold and we still find them around. U is radial, okay, Well, with these small examples and with the incremental, I would conclude the video. I would leave you to some study, and I look forward to the next video. I thank you once again.